Okay, we are talking about addition of nucleophiles onto the carbonyl compound, the aldehydes and ketones. And generally, this is what we've been doing. Use the lone pair of a nucleophile, attack the partially positive carbon because opposite charges attract. The electrons are negatively charged. The pi bond opens up. So you push the arrow, attack this carbon, pi bond opens up. You're generally gonna get an alkoxide. So your nucleophile is attached, and then in presence of an acid, this oxygen will accept the proton. So I'm just reminding you the type of reactions we are doing here. So one more reaction that we can do is making cyanohydrins. Cyano is just the CN, the hydrin is the OH part. So you're moving from your carbonyl containing compound, you're ending up with a CN and an OH, the cyano group and the hydroxyl group. So we call it cyanohydrin. So addition of cyanide to make cyanohydrins is a reversible reaction. It can go back and forth. Okay, so you're gonna need traces of the base. You're gonna need traces of the base KOH. What happens is that KOH, which is K plus and O minus, will react with HCN. The OH takes the role of a base to take out the acidic hydrogen. The CN falls off. So you're gonna make K plus, which is just gonna hang out, and then CN minus because it fell off, and then OH taking the hydrogen, you get H2O. See, OH and H gives you H2O. This is spectator is still there on our right side. The CN fell off, is this part. And then the water comes by when the hydroxide group accepts the acidic hydrogen. So you get water. So why do we need these two? We need them because that's how you're gonna make your nucleophile. You see this nucleophile I used here can as well be CN minus. Okay, so now after making your CN minus, you use a CN minus as a nucleophile, like I did here, to attack the partially positive carbon of the carbonyl, and then the pi bond will open up because the weakest of the two, one is pi, the other one is sigma bond. It opens up. You do have two lone pairs here. You end up with three lone pairs, right? But now, in presence of an acid, which in this case water will play the role of an acid. So let's say this is water. So the O negative, the alkoxide, the O negative, this molecule is just this molecule withdrawn. The alkoxide will use the lone pair on the oxygen to steal this hydrogen, and then this falls off. Okay, remember when you open up the carbonyl, you get O minus, right? Here you have K plus, which is just this K plus that comes from this acid-base reaction. So if you have O minus and you have K plus in the flask, the K plus will hang around the O minus because opposite charges attract. We call such a species a counter ion. Why is it called counter ion? It's because it's using its charge to neutralize the other charge. So it's counter reacting. So this negative charge here will be neutralized by the plus charge on the K plus, which came from KOH. So anyway, the O minus from this product will take out the hydrogen from water, and then you get OH minus. So you're gonna get OH minus. Remember, you still have K plus here, so the OH minus and K plus can combine to give you KOH. But anyway, these are byproducts. Those are byproducts. We don't need to pay much attention on that. So we pay attention on this. Okay. So your cyanohydrin will be cyanohydrin will be this structure right here. So you will have taken your O negative, the lone pair, to attack the hydrogen, to deprotonate the hydrogen from the water. You get OH minus, which combines with K plus to give you KOH. In turn, you protonated your oxygen to give you OH. So you have the CN part, the OH part. The CN part is cyano, the OH part gives you the hydrogen, so it's called cyanohydrin. Alright, so you can move from, generally you can move from an aldehyde or a ketone in presence of HCN, in presence of a base, followed by addition of an acid, which could be water, to give you a cyanohydrin. That's the general reaction we are describing in this slide. So you're moving from a ketone or an aldehyde, you use the Cn minus to attack the carbonyl like you did in the mechanism, pi bond opens up, you get O minus, O minus grabs the acidic hydrogen like we did here, you get cyanohydrin. Alright, so that's the cyanohydrin formation is not the only nucleophilic reaction you get on the carbonyl. You can also add nitrogen nucleophiles. So in fact, this reaction is called amination because you're adding amines on carbonyl. So amination of carbonyls. Okay, remember the smallest amine possible is ammonia. You do have a lone pair. That lone pair can be used in nucleophilic attack. So amines can take the role of nucleophiles because of the presence of a lone pair. This can happen either in acidic medium or basic medium, preferably acidic medium because this is not a strong nucleophile, it's neutral. Acidic medium will help to activate the oxygen of the carbonyl before nitrogen attacks. So generally, one would attack that carbon of the carbonyl, this opens up. So like we've been talking about, you get O minus, oxygen with 3 lone pairs now, and then the nitrogen still has its hydrogens. You'll have a plus charge there because nitrogen is only neutral when it's bonded to 3 bonds. So now it has 4 bonds, so it takes a plus. And now one can tell that we can do what we call a proton transfer, internal proton transfer, to get here, where this oxygen is just pulling out this hydrogen within the same structure and neutralizing the nitrogen to be neutral. So now you get here. That's called the tetrahedral product because now you have 4 bonds around this carbon. You started with 3 electron domains. Now you have 4 electron domains. So it's tetrahedral. And then now this OH can be lost by simply making a double bond. Here, this can fall off. There's a mechanism for this step. So you're gonna lose water because you'll have to lose this OH and you have to lose the hydrogen. That is loss of H2O as you make what we call an imine. So this is just a general representation of the reaction. Let's look at the mechanism, specific mechanism. So the mechanism for this summarized reaction is on this slide. So you use your lone pair, like I said, to attack the carbonyl. Okay, you attack the carbonyl. The arrow should touch the carbonyl, and then the pi bond opens up. All right. So as the pi bond opens up, you get a negative charge because now the oxygen has 3 lone pairs. So you see, this has 3 electron domains. Now this has 4 electron domains, so that's tetrahedral. It's a tetrahedral product. This reaction is reversible. And then your nitrogen still has its 2 hydrogens, so I'm gonna just put the second hydrogen here. So a base, any base, could be B base, uses its lone pair to pull out this hydrogen, and then because the nitrogen is positively charged, we neutralize it. Okay, this positive charge is on nitrogen. So clearly, to show it clearly, you have this molecule right here. Let me just show the bonds to be clear. So the nitrogen has a plus charge. So you're using a base to take out this hydrogen, and then this bond goes onto the nitrogen, and that's how you end up with this product. So that's what I was trying to show here. All right, remember this dash bond just means the metal is to the back, and this wedge means this metal is towards you. So you end up with this. So the base gained the hydrogen, so you'll get BH plus your molecule with now only one hydrogen. This could be a hydrogen or a carbon, doesn't matter. So this BH is what's written on here as base plus the H plus. So once you get this tetrahedron product with only a negative charge, you can now bring back this BH as a source of hydrogen. Okay, it's called a conjugate acid. You'll bring back your conjugate acid. It's still dancing around, floating in the flask. Use it to protonate the oxygen. To protonate this oxygen. We are just redrawing this structure right here, and then now we are protonating the oxygen. Take out the hydrogen, the base falls off, so you get your OH. But this is not stable because you have an oxygen and nitrogen close by. So you'll want to lose this hydrogen, this OH, and this hydrogen by process of elimination. So usually what you do, you use a base. Okay, so let me assume I can show this hydrogen. Okay, so you use a base, take out this hydrogen, you make a double bond, and this goes. That can happen by E2. So why is it saying loss of water? Because you're losing the H and the OH to make this molecule. H and OH, you lose water. That's why the negative here, you lose water. So you get an imine. Imines are just molecules with double bonds to the nitrogen, and then you have carbons. That's imine. Enamine, the double bond will be between two carbons, the nitrogen will be by itself. So this will be called enamine. It's coming up. Enamine is where the double bond is between two carbons. Imine is where the double bond is between a carbon and a nitrogen. Okay, so what is the application of additions of amines to carbonyl containing compounds? You always have that going on in your eye, in enzymes, in making your DNA. So many reactions in our system go through formation of imines. So if you have a substrate containing a carbonyl and you have an amine group on a big enzyme molecule, the way the enzyme will attach to the substrate is by this kind of mechanism. Okay, so you simply gonna attack. Let me show you briefly. You'll attack this. This opens up, picking up a hydrogen. So what you end up with is the oxygen with a hydrogen, just what we talked about in the previous slide. And now your enzyme will have your nitrogen still with two hydrogens. Okay, so this is the rest of the enzyme. And previously on the slide, it's this R group right here. That could be the enzyme. Okay, so it's a big, enzymes are big molecules. So the nitrogen bear plus charge because you have 4 bonds. And then part of the enzyme has a basic site where we'll pull out the hydrogen. You can pull out the hydrogen to neutralize the nitrogen. And of course, you're gonna end up with an unstable intermediate which now has NH and your enzyme. And now this one can undergo elimination of water to give you that, because like I said, a base can take out this hydrogen and then use the bond to make a double bond, and then this falls off. That's how you'll make the double bond in between the nitrogen and the carbon, the OH. The OH is gone, the hydrogen is gone, so you lose water. So this is an actual example on what happens in our bodies. An NH2 in the enzyme attacks the carbonyl of the substrate, you lose water and you make an amine. Now, let me make it even more simpler. Whenever you are reacting an amine and a carbonyl compound, shortcut is the carbonyl oxygen will go, the two hydrogens of the nitrogen will go, and that's what makes water. This double bond clicks to the nitrogen, you get an imine, right? Again, I'll give you the shortcut. Let's say you have this molecule and then you have NH2. The NH2 is bound to whatever, it could be an enzyme or carbon containing thing. The shortcut amines will lead to dehydration, so whatever I've circled should be lost as water. I just click my double bond to the nitrogen, and there you go. That's the product. That's the amine product. Of course, H2O was lost. That's what I circled there. That's an exam survival trick. Instead of going through all the mechanism, simply align the two molecules like this, you'll forever be correct. Okay? So the two hydrogen atoms from the amino groups and the oxygen from the carbonyl are lost as water. Okay. So nitrogen nucleophiles. There are a number of different imine types, compounds possible depending on the nature of the nitrogen group. So if you have amines or aromatic amines which are primary, one will always expect to get imines. Remember, imines will look like that. Okay, but if you have NH2 to OH, the name of that group is called hydroxylamine. This is how it will look like. If you are to react it with a carbonyl, you get what is called an oxime, and so forth and so forth. So I'm not gonna emphasize on these other amine products. Hydrazine will give you hydrazone, phenylhydrazine will give you phenylhydrazone. I will not emphasize on those. I'll test you on the first one. All that I've discussed here and here and here. That's what I'll pay attention to. The rest is left for the chapter on amines. Okay, these derivatives can be used and have been used in the past for identification purposes. For those taking organic 263 lab, you might be tested, or you might be exposed to the test of amines, of carbonyl compounds using amines. They give you different colors, but that's beyond this class. All right. So next we'll talk about reduction of carbonyls. Reduction is the opposite of oxygen, so it's addition of electrons. Remember what I said? Oil, rig. Reduction is gain. So when you gain electrons, it's reduction. When you gain hydrogens, it's reduction. Okay? Because reduction is gain, oxidation is loss. Loss of electrons, oxidation. Loss of hydrogens, oxidation. Gain of electrons is reduction, R. Gain of hydrogens is reduction, R. So aldehydes can be reduced to primary or secondary alcohols. The common reagents is lithium aluminium hydride or sodium borohydride. All I want you to know is that these guys will give you H- as a nucleophile. That's all. H- will play the role of a nucleophile. So assume you have this carbonyl, and you're adding either of these. So the H minus hydride, lithium aluminum hydride, sodium borohydride, H minus the hydride. Use that as a nucleophile. Attack from the back. This opens up. You're gonna get your H, your two metals, and O minus. See, you've added the hydrogen, so you've reduced because reduction is addition of hydrogen. This can go one step further. In presence of an acid, you convert your O minus to OH. That will be the alcohol. So that's the general idea of reduction. Okay. So again, the active species is the hydride, lithium aluminum hydride. So this is the base, that's the guide, that's the what we want, that's the active reagent. Now lithium aluminum hydride is a stronger reducing agent than sodium borohydride. Sodium borohydride is mild. Sodium borohydride can be used in alcohol solvents, while lithium aluminum hydride will not be used in presence of alcohol solvents because it's very strong. The H minus will simply deprotonate the alcohol. You get an acid-base unwanted reaction where you'll form hydrogen gas and alkoxide. So this reaction would kill the lithium aluminum hydride because it's going to play the role of a base to deprotonate the alcohol, which you don't want to happen. So instead, in such cases where you only have a solvent as alcohols, you want to use sodium borohydride because that's milder. But both of them, like I said, provide the hydride which attacks the carbonyl. So like I said, again, it's the hydride that will attack the carbonyl and it's gonna open up. Now, because you get O minus, the O minus gets attracted to the aluminum, so you get this complex, which I rarely talk about. And then with acidification, this whole complex will fall off and be replaced with the hydrogen. That's actually what happens. But in simple terms, what I want to tell you, because I won't ask you for the mechanism in the test, you might see it in the homework, but not the test, in which case you'll use the slides to answer. In the test, I'll want you to predict the product. I'll give you such a molecule, I give you the reagents, predict the product. So use the hydride from the lithium aluminum hydride to attack the carbonyl. This opens up. As it opens up, you're gonna get O minus, and then the O minus gets protonated by the acid. Second step is just a hydronium ion, which is just the acid. The oxygen attacks the acid, you get OH. As simple as that. Okay? So again, start with the ketone. Step number 1 is lithium aluminum hydride. That gives you the hydride, which attacks the carbonyl. This opens up. You get the alkoxide. The hydrogen now is there. This hydrogen is what attacked. And then you go one more step, which is step number 2, which simply provides the H plus, the proton, to convert the alkoxide to the OH, which is the alcohol. Notice that this is a secondary alcohol because you have two R groups. So you will have moved from a ketone to an alcohol, from a ketone to an alcohol. So ketones are always reduced to secondary alcohols. Aldehydes are reduced to primary alcohols. So let me give you an example of an aldehyde. So let's say you have this aldehyde, and I give you step number 1, lithium aluminum hydride or sodium borohydride, doesn't matter. So the hydride from lithium aluminum hydride will attack from the back. That opens up. You get O minus. Now you have two hydrogens. This is probably what was added. And then you go one more step, which is step number 2, like this step, adding the acid. The oxygen attacks the acid using the lone pair. You end up with the OH. In this case, this is a primary alcohol coming from an aldehyde. So aldehydes will give you primary alcohols. Ketones will give you secondary alcohols. So sodium borohydride will do the same thing again. Step number 1 is just giving you a hydride. You are attacking the carbonyl that opens up. The double bond does not react with the aldehyde. So this reaction is selective. Okay, the reaction is selective. The alkene does not react. Only the carbonyl reacts, even though both of them have pi bonds. So the reaction is selective. These reducing agents only affect the carbonyl and not the CC double bond. So again, we attack using our hydride. That opens up. You get this intermediate, which is an alkoxide because you have O minus. And then step number 2 is just acidification. You're adding H plus, which will add on to the oxygen. Now the oxygen has 2 lone pairs and 2 bonds. It's neutral. That's a secondary alcohol because we started with a ketone. Okay, there are other possible reducing agents. This one we call it Clemensen. It's not in your book. This one is called Wolff-Kishner. But Wolff-Kishner, I won't discuss that. It's not in your book, so ignore this slide. Okay, next time we'll talk about oxidation of carbonyls.